everyone, my name is Caroline. Today I'll be talking to you about our work on learning highly recursive input grammars. I conducted this work as a PhD student at UC Berkeley, along with Neil, who was an undergraduate student there, and my advisor, Kaushik Sen. So as you may have inferred from the title, today we'll be talking about the problem of, given a bunch of input strings or sentences, trying to figure out whether there exists a more succinct description in the form of a language that captures all these strings and hopefully generalizes beyond them. And while this has been kind of interesting in traditional linguistics, it also has applications for software engineering, including both program comprehension and testing, if these example strings actually correspond to program inputs. So today, first what I'm going to do is kind of specify the exact problem statement we're going to be tackling. Then I'll be giving you an overview of the Arvada technique, as well as the technical details that make it scalable. Finally, I'll talk about the evaluation of our technique and how it performs against state of the art. But let's start by formalizing what we're talking about. So I mentioned that we want to learn a description of inputs, or a language that describes inputs. And the description we're going to be using in this case is a context-free grammar. If you're unfamiliar, a context-free grammar looks a little like this. It essentially consists of a set of rules, where on the left-hand side of a rule is a non-terminal, and on the right-hand side of a rule is an expansion of that non-terminal. That expansion is a sequence of non-terminals and terminals, where a terminal is just a literal that appears as is in the final strings of our language, while a non-terminal can be expanded as described by its rules. So for instance, in this case, the language that this grammar describes is every string you can get by starting with that start non-terminal and expanding it until you just get a sequence of terminals. So that includes true, false, not true, not false, and essentially all these kind of Boolean expressions. So this is the description of language we're settling on in this paper. Now, given that, we can formalize the problem statement. So the problem statement we're targeting in this work is given a bunch of example strings, as well as an oracle, where this oracle can answer whether an input string is valid. In this case, it says, yes, this is a good input string. Or it can also tell us whether a string is invalid, in this case, saying this one is not. And given these example strings in this oracle, where that oracle might just be a program giving a return code of 0 or 1 on an invalid input, given those two things, our goal is to learn a context-free grammar that captures all the example strings and generalizes them as much as possible, something we'll call maximal generalization. And I'll give you an example of what exactly that looks like in a second. OK, so that's the problem statement. Example strings oracle, get a context-free grammar out of it. How do we do this? We're going to explore how our tool Arvada works by considering a smaller running example where we only have 2 input strings. And this is just so everything fits in the slide. And we assume we have an oracle that accepts programs if they're in the language of this while grammar, which I'm showing here. It's essentially a language of a simple while programming language. And the key thing to note is that while I'm showing the grammar here to give you an impression of what the oracle accepts, in reality, Arvada just sees the example strings and it sees the oracle as an opaque box that just returns true or false if an input is valid or not. And essentially what Arvada does is it takes these example strings and this oracle, and what it does is it builds parse trees for each input string. So it tokenizes those input strings into their individual characters, and then essentially builds these parse trees, this hierarchical structure over these input strings, where there are interior nodes that are labeled. And it consults the oracle very often in the process of building these parse trees. And then once Arvada has built the parse trees, it just reads the grammar off the trees, where each parent-child relationship implies a rule in the grammar. For instance, here, this subtree of this first input implies the rule that T0 can expand to while T9 do T0. while the presence of all these subtrees in both of our input examples imply the presence of this rule T0 goes to L equals T3. So thus, Arvada takes in these example strings, this oracle, builds these parse trees, and spits out this grammar, which it just reads directly from the parse trees. What you'll notice here, if you kind of remember what the while grammar I showed you earlier looks like, is that this grammar is not actually identical to the oracle's grammar. Right? In particular, it doesn't consist, there are no if statements or equalities between integers. And that's because in the examples, there were no if statement. So the maximal expansion of the examples won't include it. So essentially, Arvada does its best to generalize the examples, but it's not going to learn entirely new structures if they're not present in your input examples. So that's overview one. But what you might be wondering at this point is, how in the world do you build parse trees for inputs in the first place? And that is really the core algorithm of Arvada. So let me walk you through kind of an example of how that might work. So Arvada starts with the input examples, and then for each of these examples, it will build this flat parse tree. So essentially assigning each character or token to one child of this start node, T0. And if you were to stop at this point, the grammar you would get is just the one that exactly accepts our input strings, which is really not very interesting. So to build more complex parse trees, Arvada conducts these operations, these three operations in sequence. First, what it does is it tries to apply bubbles. So it takes a sequence of children nodes in one of the trees, and it bubbles it up, adding a level of hierarchy in the trees, and it labels this new subtree. Then to determine whether this is a good bubble, it's going to see whether this newly created label, T2 in this case, can be merged with an existing label. Meaning that if you were to give them the same label, would you get new strings that are valid by the oracle? So for instance, if we try to check whether T2 can merge with W, if you could just exchange those, you would allow trees like this in your grammar, which would allow you to have strings like this in the inferred grammar. But when we pass strings like this to the oracle rejects them. And so we decide that this merge is not valid because it allows invalid strings in the final grammar. So you keep going each time you introduce a bubble and you compare it to all the existing non-terminals. And at some point, you might check whether T2 can merge with N. And in this case, if you were to merge T2 and N, it would enable a bunch of strings like some of the ones I'm showing here. And it turns out that when you sample a bunch of these strings, all of the ones that Arvada created were actually valid by the oracle. And so Arvada marks this merge as valid. And it's going to keep this bubble. And not only is it going to keep that T2, but it's going to merge T2 and N into a new non-terminal T3. And now we've added generalization to the grammar we read off the trees. And essentially, we repeat this process. In addition to one bubbles, Arvada also performs two bubbles from every once in a while, where it bubbles up two sequences at the same time, say true and false. And then instead of checking whether T5 or T6 merge with any existing non-terminal, we just check whether they merge with each other. In this case, T5 and T6 are replaceable by each other, so we merge them into a new T7. And then we continue this process, right? And next, we might bubble up T7 and T7 into T8. We'll find that it actually is able to merge with T7, and so we relabel all of that into a new non-terminal T9. And then there's another generalization we can do by bubbling up L equals to T3. And it turns out that no other bubbles here actually enable more generalization of the language, so these are the final trees Arvada would output. So that's essentially how the algorithm works. If you look at it kind of from a code perspective, right, essentially what's happening is we start with these flat trees. Then we go through possible sequences, we bubble them up, We check whether they're valid, whether they enable a valid merge. If they do, we keep them. If they don't, we don't. And we keep going for as long as we can find bubbles that enable generalization. So while this algorithm can find a ground truth grammar, in the sense it is complete if you were to check all bubbles, it's slow in practice because, especially with 2 bubbles, you're quartic in the length of the input strings. So there are a few opportunities for performance improvements here. First of all, you can perform approximate tokenization of the inputs. We do that in Arvada, grouping together, say, lowercase characters, doing all the bubbling, and then performing a final expansion on those tokens, those approximate tokens. Also, this will progress faster if each bubble you check is one that enables a valid merge. So instead of just going through all the possible sequences, we try to determine which bubbles might enable a merge. For that, we look at 2 metrics. One is the context of sequences before we bubble them. So if 2 sequences appear in a similar context, we prioritize them as a 2 bubble, or if one sequence appears in a similar context as an existing terminal, prioritizes it as a 1 bubble. When we also prioritize the sequences that have higher frequency. And then we take like the top 100 best bubbles and we randomize their order in order to prevent all runs from getting stuck. This is one source of non-determinism in the algorithm. Finally, the other thing that's slow here is checking whether a merge is valid, right? Because you have to create all these strings and then pass them to the oracle, which can be expensive. In order to make this less expensive, we sample around 50 strings for each merge. And this is another potential source of non-determinism because if there's one invalid input, we reject the merge. That might differ between 2 runs. So let me now give you a taste of the evaluation. We evaluated Arvada on 11 benchmarks. The first 8 were kind of perfect benchmarks in the sense that the oracle was a parser for these ground truth grammars that accepted only inputs in these grammars. And the train and test set was conducted by sampling such that the test set is the maximal expansion of the training set, or rather the training set can maximally expand to the ground truth grammar. So we know we could get perfect recall and precision on these benchmarks. We also look at 3 kind of messier benchmarks where the oracle is just a regular program that returns a 0 or 1 return code. And the train and test set are just conducted by random sampling of some grammars or generators. So the training set doesn't necessarily mean that we'll be able to maximally expand to all the inputs accepted by the oracle. And as that baseline, we compared to GLADE, which was in PLDI in 2017, which has the same problem setting, but rather than combining all of the input examples as it's building the grammar, it starts by generalizing each individual example as a regular expression and conducting some merge only after all that generalization is done. To give you a taste of the results, I'll show you the F1 scores that were achieved by these tools. The F1 score is the harmonic mean of precision and recall. And what this plot shows, all the dots are 1 run of Arvada. We conducted 10 runs to account for its non-determinism, and the stars are a run of GLADE. And what you can see is that the dots are generally quite above GLADE's performance. On average, we have a 3 times increase in F1 score. Most of that comes from the 5 times higher recall that Arvada gives, and recall is something that measures generalization. So we really generalize better than GLADE. While it looks like our slowdown might be due to some of the complexity and the fact that Arvada is presented in Python rather than because it's conducting a lot more oracle calls. For curl, we see that the fact that Arvada performs less well here is driven by the runs having low precision, which means that Arvada has overgeneralized. This kind of makes sense because the URL language that curl accepts is regular rather than having lots of recursive structures, which is what Arvada is looking for. And also the 2 runs on Node.js where Arvada has poor performance are driven by very poor generalization, so low recall, which looking at it manually, it looked like Arvada had some trouble learning the regular expressions for tokens in this benchmark. However, on the benchmarks where Arvada has 100% precision and recall, for instance, this is a run of while where it got high precision recall, you can see that the grammars it outputs are actually quite concise. Here's a one for while, and here's one for the best runs of JSON. So with all that being said, today I talked to you about this problem of learning from a set of example strings and a Boolean oracle, a context-free grammar that maximally generalizes those examples. Our Arvada tools works by building parse trees of inputs and reading grammars off the trees, where those parse trees are built by a sequence of bubble and merge operations. And we found that this had over 5 times higher recall, well, generalization, than the state-of-the-art GLADE, while only achieving a little less precision, which resulted in all 3 times higher F1 score on our benchmarks. Thanks for listening, and I'm glad to take any questions.